Okay, so I'm going to start off by talking about magnetic resonance imaging technology in general. So before I started working in this field, I thought it was just one sort of data you could acquire. And actually, there are many, many different kinds, and the technology you want to use when you analyze them is vastly different. I'm then going to talk about diffusion-weighted measurements, which is the sort of data I deal with, and in particular, high angular resolution diffusion imaging, because you want to figure out what sort of resolution you can get out of directionality in the data. I'm then going to adapt a sort of popular non-parametric estimation method to get an estimate of this orientational distribution function. But then I'm going to ask myself, what do we actually want the data to tell us? Because we're not really interested in this diffusion estimate of the PDF directly, but there's certain characteristics of the data we want to find out. So after having gone to the trouble of setting up the estimation problem, I'm then going to be estimating summaries of this non-parametric estimation. So it all kind of reflects the things I can do. So non-parametric estimation, I know how to do shrinkage. And after I did shrinkage, I had to do something more because I wasn't getting out everything I needed to know. And I can only do one more thing than shrinkage, and that's averaging. So we're going to get to an averaging problem after we've done shrinkage. Likelihood, regularized likelihood, too hard for me. I get collaborators to do that. And finally, I'm going to discuss how these summaries actually relate to features of the diffusion in space, which is what we actually want to know about. Okay, and then I'm going to apply it again to some real data and show you that these non-parametric summaries can actually tell us when these spatial features are part of the data. So the proof of the pudding lies in the eating. So just to give you an overview of my understanding of MRI, MRI technology is based on using a very powerful magnet. That was my first understanding of it. So you get a 3 Tesla magnet or bigger. They're very expensive pieces of equipment. And what you do with this magnet is you use the magnetic field to align water molecules in certain directions, and then you let them to get back to the natural state. And a radio wave makes the molecule resonate, and during this phase they absorb energy. You then apply extra field gradients to make it align with different directions and see how it goes back to its natural state. And after you've done this, you basically have a scanner that measures the energy released by the molecules, and you use this to try to infer properties of the material you're imaging. So I'm not going to get more technical into MRI because I'd probably trip up and say lots of stupid things. I think the important thing is to realize that all of these things are a bit of a simplification. When you say you whack them and sort of make them align in a certain direction, that doesn't happen perfectly. And so you could spend a lot of time trying to understand what directions they're actually getting aligned to. I'm going to use a slightly simplified description in this talk because it could get very complicated. Okay, so that's what a typical MRI scanner looks like. So whenever you start working with some of these people, they will take you down to their scanner and show it, probably because it costs several million pounds. I've never been in one myself, and I wouldn't do it, I think. Okay, so why were these people interested in involving me in the first instance? Well, my expertise, apart from wavelets, is in complex valued objects. And what people found out in the 1980s, or figured out from theory, is that once you look at the MR signal, you're actually measuring the Fourier transform of the density directly. So you actually end up with a measurement of the Fourier transform, and that was discovered independently by 2 different groups. One of them Swedish, of course, given Swedish scientists are the best, as I was taught as a young child. Because of that, to estimate the density, we can just calculate an inverse Fourier transform. Now that's a simplification. It's a simplification because depending on the acquisition procedure, you're going to have the data varying in lots of nasty ways, not to do with the actual Fourier transform you want to estimate. So for instance, you could build all of K-space, where I'm now calling the Fourier variable K, in a single shot, which is called a single shot EPI, and that will remove lots of horrible artifacts in movements, which will be due to your heart beating, or you breathing, or doing other things you're not supposed to do when you're getting scanned for 10 minutes. Or you could build it in several shots, where you'll have more of these artifacts, and then these will have to be dealt with by the actual analysis. Or you could use the actual acquisition scheme to improve your estimation procedure. So they've been trying to sort of fiddle compressed sensing to fit a spiral acquisition scheme in Stanford, for instance. We're going to be talking about single-shot EPI, where you don't have so many movement effects, and I'm not going to be using the actual acquisition to do any special fancy linear algebra with you. Okay, so my particular field of interest is diffusion-weighted MRI, and this measures the diffusion of water molecules in biological tissue. And molecules tend to move mainly in the direction of the fibers because the myelin around the fibers prevent them from diffusing in other directions. So this is a structural understanding. You're getting a direct mapping of how the nerves are in your brain. This is not based on your interpretation, right? So some of these other measurement techniques, you're going to need to input more of your understanding to interpret the signal, but this is directly structural.
Is what they do in brain imaging very different from imaging the rest of the body?
No, not really. I haven't looked at hearts or other parts of your brain, but you can, no, you can use the same technology in different parts. Other kinds of magnetic resonance imaging which are popular, and I'm kind of mentioning them just because when I first got into this field I had no clue whatsoever what these different kinds of imaging were like, and it's kind of nice to know how they all compare. So another popular technique is MR angiography, where you basically administer a paramagnetic agent to create contrast, and you look at the arteries that you're imaging and see if there's been a narrowing of the artery or if the wall dilations have sort of happened or not. What people who do statistics tend to look at is functional MRI, and that's because we're all used to treating lots of time series. So the brain is now scanned at a low resolution. You don't get so good spatial resolution in your picture, and you get out lots of time series measured at each location in the brain. And this is based on the bold effect, so it has to do with the blood oxygenization. And this is due to increases in neural activity. And I mean, they're inventing more of these as we speak, right? And I think that's one of the exciting things as a statistician, because you could be the first person to think about how to analyze a particular kind of data. I don't even have to be that good, right? I can just be the first one to do it. Okay, so what does the data actually look like? So I've got here just a few slices of typical acquisitions of the data at a given height across space. So what you see here are direct measurements of the diffusion of water in a specified orientation. And what people have done is they've done an inverse Fourier transform to return from K-space to get back to the spatial domain, but there is structure remaining which is actually due to Fourier domain understanding, because you measure in different orientations in the Fourier domain locally. So when you do the inverse Fourier transform, that's really at a larger scale. And that's why you end up with lots and lots of these different pictures associated with the same pixel or voxel, but they're actually associated with diffusion in different directions in the Fourier domain. So you want to understand a person. I was going to take me as an example, but I think I'm too embarrassed to show myself on the big screen for a long while. Okay, so let's actually get down to the nitty-gritty of the problem, because that's how we can understand what's actually going on. So we'll start by denoting what we want to measure, the theoretical Fourier transform of the effective spin density by A of k. That's a curly A of k. K is the Fourier variable. And what we actually want to say is something about the spatial properties of this spin density, which we denote by little a of x. So that's just an inverse Fourier transform. And in theory, if we had the exact Fourier transform in K-space, we could end up with a real spatial transform and we'd be happy. But things are complicated slightly, as I said, by the fact that you tend to image slice by slice in z, the loss component of x there, directly in K-space, but for a given direction, which we should here denote by q. So even if you do the sort of global spatial inverse Fourier transform, you end up with an indexing associated with the orientation locally in Fourier space. So that's something to keep in mind. You end up with a complex valued observation because you have a Fourier transform. So even when you do the inverse Fourier transform, because of the way things are done, in general, this will be a complex valued observation. People who do this sort of imaging that I'm discussing will fix to a single shell. So when I talk about the direction, you could actually have more than direction here. You could also have different heights locally, and that adds extra structure. And these will be sort of modulated by the strength you're using for the magnetic field coil gradients, etc. And we're only going to discuss estimation for a fixed value of this vector. And finally, to normalize this density, you're going to measure the value at 0, because basically that A of x should integrate to 1 because it's a PDF. And so you know that capital A of 0 has to be 1. So you end up with capital N observations of the actual density plus some estimates of the normalizing constants. So this is basically, I'm being slightly nasty here, I'm sort of jumping notation slightly too quickly. I'm going to explain why we don't look at this complex valued object at all, but you take its modulus to remove phase variation. And you complement that with normalizing constants modulus. So I'm jumping notation slightly too quickly. So this is going to be replaced by AQ of AK of QL. These are going to be thought of as A of QL. And these are A of 0, but there has to be several measurements of them because you need to have a good estimate of the normalizing constant. Well, I say so. Not necessarily true, right? So people who are physicists and have thought about this say that the measurements XL plus IYL have to theoretically be real valued. So they say that the symmetry of the spatial object, I should probably use the pointer. They say that the symmetry of the spatial object is such that once you do its Fourier transform, it has to be real valued. There are theoretical arguments for why that is true. But as I said, you actually get a complex valued object due to phase variation, and this is mainly due to your heartbeat. So what I was jumping quite a little bit too quickly when Richard asked for the ACE appeared, well, what people do then to avoid this phase variation is they just take magnitudes. And in fact, in most scanners, this is done before the data is read out. So if you want to get hold of the complex valued objects, you actually have to get in there before the scanner sequence. And what we then do, because we know this is a PDF, it has to integrate to 1, is we normalize the measurements by using these measurements as 0, and we take their average as an estimate of the typical value of 0. So it's method of moments estimation. Okay, so to sort of go back, we now have lots of these AL, which are all associated with a vector Q, which has the same modulus, but is associated with a different orientation. So we have lots of measurements on the sphere, and we'd actually like measurements on the sphere in space, not measurements on the sphere in Fourier space. And that's kind of a hard inverse problem to calculate because we really have undersampled quite substantially in the Fourier domain. And to make the problem even nastier, the number of observations you typically have, if you're really, really lucky, is 60. So sometimes in experimental scenarios, you'll see people whacking out 450 measurements. That will not happen in a medical facility. They started out by just taking 6 because they were feeling really adventurous. But to get some sort of sense, you really need at least 60 observations. And to me, that is basically saying one fact. You cannot expect to determine everything about the spatial density. You can only determine some features of the data. I mean, that's fairly obvious. I'm sure none of you are going to argue with that. So to show you some pretty pictures, what we would really like to understand in space is how does the diffusion densities look in space at some fixed radius, namely the radius associated with the right scale for the diffusion of water molecules. And I'm now showing you some typical distributions we might expect to get out in space. So first here we just have a single nerve where you see a single diffusion where it's easier to diffuse along this direction and very hard to go the other directions. That's a kind of idealized scenario of what people would think these nerves actually look like. But of course, human tissue is nasty, so you could end up with things which is highly ellipsoidal, where you don't actually get a nice radial structure in the other two axes. You could have crossing fibers, where you have several fibers. Or, and this is a bit harder to sort of get your eye around, this is actually not symmetric. So you have a shift in a symmetry where it's slightly closer to that end rather than the other end. So that could be a start of a forking of fibers, etc. And all of these are microstructural features which you would use later on when you're trying to create a map of how your brain is structurally connected. So all of these local estimates at each fixed location is just the first step to understanding what's the structure of your brain, how are the voxels connected together, because that's what people want to know. And they really don't want to know what's the structural connection, they want the functional connection. You know, how is that bit of your brain functionally connected to that bit of the brain? And this is seen as sort of one piece in a big inference problem which would require many more sorts of measurements. Okay, and just again for you to get an idea of the sampling, typically people who have really good data have 60 directions. Because of the Hermitian symmetry of the Fourier transform, I allow myself to double over for numerical accuracy. So both of these are 120 measurements which don't have more degrees of freedom, but once you do the procedure you would get better numerical accuracy because you use the Hermitian symmetry to double over. And as you see, these are not super dense, and the way people place these measurements are actually regulated by physics understanding usually. So how would the density look in the Q space if it actually corresponded to the pictures we just saw? Well, if you had a Gaussian that we saw initially, which had one nerve peak with two eigenvalues being, well, there the two eigenvalues would be smaller than the other because you're sort of larger than the other, because you're easier to diffuse in the other direction, but you would end up with a band in Q space because the eigenvalues, you would get inverses once you did Fourier transforms. If you had something which was ellipsoidal, you'd still get a band, but you'd get variation along the band. If you had something which was two nerves, you would end up with two intersecting bands which would look like a square. And something asymmetric would be a band, but the structure from the belt of the mid of the sort of circle here would be different on the two different directions. But you have to be quite careful, as I'll explain later, because the Hermitian symmetry of the measurements are going to make things slightly awkward. Okay, so we have too few measurements, and we want to understand the structure of the diffusion in space. What are we going to do? Well, the first thing people did was they said, okay, the PDF is Gaussian. Okay, it has a mean 0, it has a covariance matrix with 6 entries. I need 6 measurements and then I can estimate these 6 entries. That's what people did at first. And this was found to be too simple. At least 1/3 of all the voxels in your brain will fit very poorly to this model. So you can even tell when you have very few measurements. They then applied what they call the Gaussian mean mixture model, which I wouldn't call that way because you're actually modeling the mean of the mean of your observations as a Gaussian mixture. And this has the issue that it's not identifiable, and certainly there are also problems because the interpretation is not clear to me. How do you know when you have a certain number of bumps or Gaussian peaks that you should think of these as the same number of nerves? If you have something asymmetric, this will take 2 bumps to actually represent, right? But do I want to think of this as 2 different nerves or just as a single nerve which is asymmetric? There are 2 non-parametric alternatives to these models. So the first was sort of come up with a colleague of mine at UCL, Danny Alexander, which is PASS-MRI. This makes assumptions about the spatial structure of the PDF and tends to create estimates in space which I think are slightly too peaked. I think Danny would agree with that. So you make a basis expansion in space and you Fourier transform, and this has an inherent smoothing associated with it. So there's a risk of removing features because you don't use too many basis functions, and that means you actually smooth. There's something which is known as Q-ball, which is based on theory for going between functions on the sphere, and where they try to calculate the average diffusion across all radii in space. So they're not just looking at one radius the way this does, but it's looking at the typical orientational structure across all radii you could have in space. And of course that tends to flatten out the distribution because you're looking at the average across all the different scales, and you want a set of scales. So these kind of correspond to the state of the art of estimating properties of the diffusion at the moment. I think PASS MRI, oh, it's a colleague, so I'd say it's best, right? So just going, before we start going and dipping into the inference problem, what can we actually ask of the diffusion? Well, firstly, how many peaks are there? How many nerves are there really in your structure? And how radial are these peaks, or have they started becoming ellipsoidal? Because that is a sort of a preset to other features happening once you start looking at lots of voxels together. Because once you start to connect the dots, you look at the estimates of local orientation and preference at each voxel, and you try to connect them all to get a sort of an idea of connectivity. Then if you start having ellipsodality, it could be a precursor to branching. So it's important to get out how radial are these peaks. So if they're highly ellipsoidal, that could be a precursor to branching. And as we just saw again, another question to ask, asymmetry could also be a feature which is a precursor to a different kind of branching, and it's also something we want to ask the data. And of course, whenever I attack an inference problem because I'm lazy, I always first ask myself, can we really answer this question? Because otherwise I'm going and having a cup of coffee instead. So I'm going to answer some of these partially, and you will see that not all of these features can you really determine very well from the data. Okay, so the problem with the existing methods, if you want to get out these microstructural features, is that sometimes they usually smooth uniformly. So they try to estimate this density either in Q space and then do something clever, or return directly to space. But there's an inherent bandwidth associated with only using a few functions. And most of them smooth uniformly, and they smooth too much. So you're not going to get that much power out of your test once you design it if you start off by smoothing out everything that's in there. So sometimes we don't want to smooth a lot, sometimes we do. And I say strongly all the time, I don't do wavelets any longer, but then I seem to every now and then shove them out of my sleeve. So apologies to listeners who've been exposed to me before. I am going to do a little bit of wavelets here. And of course, we now need wavelets on the sphere to be able to estimate the density. And that's something which has puzzled geophysicists for a while, and they're very good at sorting these sorts of problems out, so we'll turn to those solutions. Okay, so if I want to do a non-parametric estimate on the sphere of the density using something like wavelets, I need to find a good way of averaging and differencing. That's the basic problem. Unfortunately, we have observations that have been decided in a certain pattern by the physicist, and they are usually nothing like a regular grid. Okay, so the obvious source of illumination is Schroeder and Sveldens, who designed lifting on the grid back in 1995. And it's a very, very simple algorithm. You start by calculating distances between all the different points. You get a notion of how far apart are your observations. And you define something which really corresponds to a Haar wavelet. It's the simplest form of averaging and differencing on the sphere. So you calculate a set of a sort of minimum or coefficients associated with the least distance in a sequential fashion. So you start out at first and you just find the index at scale 1 here, if you start out at first, was associated with the point closest to point I. And having done that, the trivial thing is just to look at how smooth is the function. Well, if it's super smooth, if you take the point and you look at its nearest neighbor using this distance, then you should get 0 out. This is the Weyler coefficient. And with the scaling coefficient, what's an average? You take the point, you look at its nearest neighbor, you rescale for orthonormality, and you end up with scaling and Weyler coefficients. So there is a problem here. So usually when you implement lifting, you would subsample, so you get a non-redundant transformation. I am not going to do that. The reason I'm not going to do that is twofold. Firstly, if I subsampled, I would not get a basis. Why would I not get a basis? Well, basically, the relationship of being the nearest neighbor on the sphere is not sort of an equivalence relation. You know, if that point is nearest to this point, then there might be another point which is nearest. So if I subsampled, I would not be able to do perfect reconstruction. So it would be a bad idea. That's reason 1. Reason 2, everyone knows who does wavelets. If you subsample, you lose numerical accuracy because you have misalignment between structure. So I have 2 reasons not to subsample. Well, actually, in reality, the first time I implemented it, I did subsample and I couldn't reconstruct my function, and I spent the whole Saturday swearing over it. So you end up with a redundant transform, too many coefficients, and it's not associated with a regular grid in a single scale, but people have dealt with this in 1D. Many, many people have dealt with this in 1D. There's work by Peter Hall. I like to cite the work by Sofia Olhede et al. And all of this directly can be translated over. And I apologize, it's slightly unclear when you do the first scale, because these should really be A of I and A of B. But this is just set up like that so you can get a recursive representation. Okay, so I want to show off that I can do the spherical plots. So if you wanted to look at the actual basis functions associated with the first few levels at a given scale, here I've chosen the number of scales I use to be 3. And that's the first Euler coefficient at that location. That's the second Euler coefficient at that location. So j is equal to 2, j is equal to 3, and that's the scaling coefficient representing the smooth structure at that region. So it all behaves maybe not quite as nicely as some wavelets, but clearly you're differencing and you're averaging. So it's doing something of the right sort of behavior that you would expect. Okay, I'm going to go over this fairly quickly because it's just algebra and we can all do algebra in our sleep. I'm sure this would be a nice little problem for an undergraduate. So the problem now is there's no undergraduate in the room, so we can all relax. The problem basically is that the observations are not Gaussian, the observations are not chi-squared, and the observations are not non-central chi-squared. If I squared the observations, I would end up with aggregations of non-central chi-squareds, but I wouldn't be estimating the thing I'm interested in. So I don't want to square it just because the math would get easy. So I think that's giving up. So with the procedure I have just described, one can analytically calculate that the expectation of the Euler coefficient, where rho here is just plus and minus 1, is just an aggregation of these functions, which are functions of Bessel functions corresponding to Laguerre functions, when that index is an integer, and the functions both of the true signal I want to estimate and the noise. And generally you assume the noise has the same magnitude across all coefficients. And similarly, you can get a neat expression for the scaling coefficients, again in terms of these functions, which would be Laguerre functions if that half was an integer. And you can calculate the variance, again directly, which again is not constant now when we calculate the Euler coefficient, because the variance of a Ricean variable depends both on sigma and on the mean. So you end up with, depending on the signal to noise ratio, a different noise magnitude as you go across observations. So you can directly calculate theoretically what these would be as you go across all scales j and points you are on the sphere I. And I've simplified the expression here because it should really be a sum over a, k, etc. But I've sort of said it's locally smooth, so blah, blah, blah. And we get an order 1 term here, which is generally not large, but has to do with the fact that we're using the redundant transform and that sometimes the nearest neighbors don't match. And when the nearest neighbors don't match, you might end up with something more in here, which we're going to ignore. So in the lifting school of thought, there's a tradition of ignoring this correlation. Just have a look at the Bernard Silverman paper with Guy Nason and Morten Janssen. If Bernard Silverman ignores it, I'm going to ignore it because he's cleverer than I am. Okay, so most transform coefficients are small, so thresholding or shrinkage is appropriate. And you can figure out, as I'm going to show in the next slide, how to actually do this. So this is some references for similar work for non-central chi-squareds, and this is the way to do it if you have a Ricean distribution. So I'm doing some slight simplifications. Depending on the signal-to-noise ratio, it's appropriate to use the usual median absolute deviation estimator to get out the scale estimate. The scaling here is going to depend on what your value of A is. In most signal-to-noise ratios, it's acceptable to use a normal scaling. Sometimes you should use a slightly smaller scaling. So I'm choosing to use the normal scaling because that's going to, sometimes you will use a larger scaling. It's going to end up with a larger estimate of the sigma, which I find acceptable for various reasons I'm not going to go into here. The second thing you need to do once you're doing this estimate, and you need to do it in the right order, is to estimate the scaling coefficients V. Because you're going to need them when you estimate the Weyland coefficients. And because you want to get rid of the noise floor of the Ricean distribution, basically you get a constant added just from the noise to all observations. You do thresholding, which turns out to be soft thresholding. So you just remove a constant and you estimate the scaling coefficient. So you remove bias. This is not really a thresholding exercise, it's really a bias correction exercise. Then, once you have an estimate of the local mean, the variance, you can estimate the variance of the Weyland coefficients and just plug in all of your estimates in the formula, and you end up with an estimate of the local variance. And once you have that, well, you know, anyone can estimate Weyland coefficients with estimate of the variance. So you just do normal hard thresholding to get that with estimates for the Weyland coefficients. And because you really don't want to miss any high frequency structure, it's really best not to threshold coefficients singly. This doesn't actually work very well at all in practice unless you have super high compression. Normal Weyland thresholding only works coefficient by coefficient if you've got a really good Weyland transform adapted to your signal. It's a lot better to use local thresholding and look at values of nearby coefficients. And that's, you know, there's a host of literature for that. So I could show you simulation results and the good performance and all of these, and we could all say, oh great, we have a good estimator of Q-space, the Q-space density. It's actually useless. We don't want to know anything about Q-space. I was sort of happily bumbling along, phoning Michael Albright up and saying, I've got this great estimator. And he says, well, I don't really care. Okay, so what did we really want to answer? Well, it was the questions of the previous slides. Basically, we want to answer, is there one peak or two peak? Is it locally ellipsoidal? Is it locally circular? Or is it asymmetric? That's the questions we wanted to answer. We didn't want a good non-parametric estimate of the Q-space density. So we're still in Q-space. Even if we removed a lot of the noise, there's quite a bit of noise left. Okay, so I said I know how to do two things. I can do thresholding and I can average. Okay, so I have to average. I tried thresholding. It got me somewhere, but not everywhere I wanted to be. Okay, I think I'm actually going to skip forward to the next picture to explain what I'm at. Actually back. Yeah, this is the picture to go to. So we have estimates of these things. We have estimates of the orientational preference in Q-space. And what we now want to ask ourselves is there one peak? Is there two peaks? What's the structure of the single peak? So that's one peak. That's one peak which is ellipsoidal. That's two peaks. And that's an asymmetric peak. And I want to average. Okay? So I looked at these and I thought, well, the obvious thing to do is to average here. I would look at structure along the great circle, and then it would be fine to average perpendicular to the great circle because I have the same structure, so there wouldn't be any bias. Here again, I wouldn't get out exactly the right value for the perpendicular structure, but I could still compare how that was compared to the magnitude along the great circle, and here I would get substantially different behavior. Okay? We need a new coordinate system that reflects this understanding, so I'm allowed to average, which is the only thing I'm capable of doing. Okay, so to average, what's the most important thing in those plots? Well, it's what is the location of this great circle. So what we start with when we're trying to infer properties of this distribution is start with what's the location of the peak, what's the most dominant great circle in Q space, or the location of the peak in space. And we know for commonly these types of models, once we start estimating locations, we're going to get super consistent estimators, which are, you know, order n, blah, 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 blah. So we start out by just looking at the maximum of the peak, and we end up with an estimate of the location of the peak or the orientation of the peak, which I will call just epsilon 1 hat. And we can determine a full eigensystem by just looking at the other two eigenvectors from calculating that matrix and its eigenvectors. And then, once we have this new coordinate system, which is going to measure variation relative to the dominant great circle, which we found by looking at the maximum peak, or the maximum dominant great circle, which is just calculating a maximum, we have some new notation. So we now start to map out the density in terms of structure along the great circle and structure perpendicular to the great circle as you go along the great circle. So that's going to get us two sets of positions, namely one which is along the great circle, which is just a linear combination of these two second vectors, and all of the vectors which are perpendicular as you go around and start going at the curves perpendicular to that great circle. That gives us some new notation. And we can then look at the structure again. We can unravel it. So now I see where I can average. It's very clear, right? So at the first, we only had the single peak, which was a single great circle. As we start mapping that out in beta, which is along the great circle, and alpha distance from the great circle, we see that it's cool to average as long as you go in the beta axis. Here, we have the situation of two peaks. Well, we're going to have heterogeneity as we go along the beta axis, but this is going to give us a tool of differentiating these two structures. Here, we have an ellipsoidal structure. We're still going to have dominant great circles, but there's going to be variation along them. And finally, we have the thing I was hitting for, my asymmetric density. We have different decay to the left and to the right of the great circle. And because of Hermitian symmetry, unfortunately, these switch over. And because we're looking at real data, we don't know where we're starting. But still, there is structure. We can see it. So what you end up defining as useful statistics, which you're going to create your statistical test from, is just looking at typical curves along the great. So you look at the curve along the great circle. For the single peak, it's constant along the great circle. If you have two densities, it varies along the great circle. If you've got one, but which is changing like an ellipsoidal structure, there's some, but not as much variation. And with asymmetry, there's going to be some enforced variation, but not a lot. And then you look at the average perpendicular. Well, there's a big difference in the variation along and perpendicular. Here, where there are two peaks, there's actually more variation along than in the perpendicular. Here, there's more variation in the perpendicular than along, because it's really one peak, but it's ellipsoidal. And here, I've done two different averages, again, to show you what asymmetry is all about. So in the average perpendicular curves, you see that this is averaging across the full circle. So it's symmetric because of the Hermitian symmetry. But the asymmetric case, where I only average half, you here see that there's a different decay, so that you can differentiate between the two structures. Okay, so this is all very neat, and it's going to allow us to average, and I'm going to do some hand-wavy arguments to get out distributions for us in a little bit. But there's something one really has to understand when sort of presenting this representation of the data. Okay, this does not have typical degrees of freedom you would expect in an image, right? Because there's some points which are here which should be mapped to the same point and things like that. I've unwrapped the sphere, but actually all perpendicular great circles will pass through the same point, namely the point perpendicular to the great circle. So the degrees of freedom are not like in a normal image. Don't think that even for a second. Well, I did, obviously, otherwise I wouldn't make such a point of it, would I? Okay, so the final visual, over-stressing what the structure is like. Here we have a great circle. I'm looking at variation on the great circle. I'm then looking at decay from it over structures which move away in terms of this alpha parameter. And you can have lots of different great circles, but they all pass through this point. So the degrees of freedom is not going to be the same as you average here or as you average there. So that should be, even for someone who's visually challenged like me, that should be pretty clear. Okay, so given I've now defined a new coordinate system where I can average easily, it makes sense to define the theoretical quantities which this averaging would correspond to. And this notation should make no sense to you because I didn't have it in the previous slide because it was discrete there. But here is just a continuous equivalent of having these vectors which go perpendicular, a certain distance perpendicular, and some mapping on along the great circle is beta. So I'm here just averaging the perpendicular structure by going along the great circle. It's just my way of parameterization. And because I'm an evil frequentist, and I was brought up in the old school, I'm now going to do hypothesis testing. I think I do this mainly because I think I can annoy people. I used to sit next door to a Bayesian who was very fundamentalist. So we're first going to consider the hypothesis of isotropic versus anisotropic diffusion. So if you have an isotropic diffusion, then you have a constant on the sphere. So I'm just going to compare a hypothesis that everything is constant versus the fact that I have a single peak. And then as a second stage, I will compare the assumption that you have a constant versus multiple peaks, because these are going to look quite different as hypotheses. So we start out with saying, okay, it's constant, and I'm going to need some assumptions for which the averaging makes sense. And I'm going to say, well, if I have something which is like an ellipsoidal diffusion, then I'm going to be able to calculate these with success if the eigenvalues have certain relative magnitudes. So in a way, I'm just common mathematician sense, I'm now dressing up something that the physicists would all have modeled as Gaussian, but I want it to be slightly looser in the assumptions I make about the PDF to be able to be allowed to calculate these averages. And it turns out if you estimate the diffusion using the Weyland method or any other method to start off with, it makes sense to look at the average perpendicular estimated diffusion at its maximum and compare it to the minimum, and look at the diffusion in its maximum on the great circle and the minimum. If this is isotropic, this is going to be like 1 plus an order statistic, because you're looking at maxima and minima. If this is a peak, what's going to happen? Well, there's going to be a great deal of difference as you start going perpendicular, because if you had a peak, you had this great circle band and then decay around it. So this is going to be a method we can use to distinguish between isotropic and single peak diffusion. Afterwards, when you've done this test, if you want to distinguish between the isotropic and the dual peak, you would just start looking at structure along the great circle separately and compare it with the isotropic case. So that's the first test statistic you could use to determine its properties. Secondly, something I did believe in when I started this project quite firmly is you need to relate the new statistics you invent to properties people are used to looking at, because otherwise they're not going to be very happy with you because they can't interpret what you get out. So having estimated the diffusion, and now I have this little perpendicular here because I obviously am using inconsistent notation, these should both be just averages and no perpendicular. These are the average structure which have averaged at the same distance from the great circle. Then this is measuring what's the difference in the magnitude on the great circle versus going the maximum distance away. So that one is just, I choose some axes where I decide some magnitudes, but this is basically the point perpendicular to the great circle. And if it indeed is a unimodal diffusion, then you'll have this band structure we saw before, where you have things on the great circle that decay away. Then indeed, this is going to be, once you calculate this whole ratio, this is not going to be equal to that, but you're going to end up with a small value because you're taking logs and it's all PDFs. So you can interpret this psi as the degree of anisotropy from the average perpendicular circle, and it turns out just to be a ratio of things people are used to looking at, namely the apparent diffusion coefficient, which is looking at the apparent diffusion in a certain direction, with one major twist, namely we've averaged here, right? So we have these average perpendicular structure rather than having the non-parametric estimate of the diffusion without averaging. So that means that this parameter is anatomically interpretable, and people are used to looking at features like these from the diffusion. Ellipsoidality, again, can be determined by comparing structure along the great circle. I'm sure the formula are not so interesting. I had to do some twists for robustness, but you end up with a statistic whereby you can determine whether something is ellipsoidal, i.e. variable along the great circle, or not. And finally, I don't know why I took a fancy to the asymmetry, but I did. You can define a statistic which allows you to determine how asymmetric the density is directly in Q space, this funny space, but you have to be quite careful because you have to know where it flips over, right? Because it's asymmetric and decays more in one direction than the other for half the circle, but because of Hermitian symmetry, it flips over and goes the other way for the other half. So I use a simple maximum to figure out which I can average. So again, I sort of look at each point on the great circle, I start comparing the decay, I go around the sort of full half, because again there is a redundancy, and I find the point where it's the most difference, because that has to happen when you're sort of midway, sort of going through the full circle, and then I average locally to get out a test statistic with less variance. Okay, so there needs to be plots to show I've actually done simulations. So I simulated from a number of these diffusions, and we can now look at the results a little bit, plus my distributional approximations and conservative estimates, which aren't always super great. So here we see a number of plots which are all unidirectional diffusions. And this is all based on that TN statistic, which measured the difference between the ratio and magnitude of the maximum and the minimum on and off the great circle. And what you can see here is that you get large values for this statistic for, say, typical Gaussian, asymmetric Gaussian, even an ellipsoidal Gaussian, and these are all variations on that theme, with the major exception of this curve here, which is something which has two tensors in it. It has two diffusions in it, so it's not clearly unidirectional. So if you have a look at the statistic under the null, namely you have an isotropic diffusion, then you get the solid line you see here, and depending on what approximation you make to the density, you get the solid line, or you can have a conservative estimate of how large it could be, and you get the dotted line, which is super conservative. But if you use this, you're sure to include, all the tail values.
Can you say some more about how you got the distributions of the test statistics under the null?
So it's a combination of figuring out how many things you're doing maxima over and the effective degrees of freedom, combined after that with averaging. So it's Taylor expansions, summing, and looking at properties of maxima.
So eventually this will lead to asymptotic arguments?
Small parameter arguments, yes. The signal is usually bigger than the noise.
Okay, and at the moment we are talking about data from a single
yes.
pitch, right? So
yes.
the n equal to 6 or 60 doesn't play a role here?
No, because it's sigma we're looking at, not n. Yeah, if it was n, I'd be in deep trouble. That's extremely correct. And similarly, we can do with the ellipsoidality and the asymmetry statistic. And unfortunately, my estimate of the density for the asymmetry is a bit wonky because it's actually stretching out very far, and I should have picked a smaller bandwidth for the estimate. There is nothing in the zero region here. And indeed, this is very easy to catch an ellipsoidal versus these are all different versions of highly directional anisotropic diffusions. And this here, I'm not going to discuss in details, it has to do with what happens when you misclassify 3 or 2 nerves as one nerve, and what is the distribution then. And basically what you find is when you misclassify a nerve, you end up with really wonky shapes of the distributions, which is to be expected, right? And likewise for the asymmetry, this is really hard to detect, as we might have expected with 60 measurements on the sphere. So the solid line here is the approximation to the density. The thin solid is the true from simulations. As you see, they really overlap quite well. And the same for an ellipsoidal distribution, but which is not asymmetric. But the power is really poor. So all of these are different versions of asymmetric diffusions, and it's going to be very hard to catch them based on these simulations, because most of the values do not become large enough. And this is like an inherent problem with trying to get out fine scale structure from 60 measurements. You can discuss this more carefully in terms of thinking of the approximation properties you're implicitly making. Okay, so I have to show you some brains, because otherwise you came for the... Usually people have spinning atoms, right? Well, I can only show you brains, and they're not spinning. So these are first just raw test statistics for a single slice of a brain at a given height, based on the actual directionality of the data. And indeed, you expect to see these shapes here. I showed them to my contacts at CMC down in Hammersmith. And basically, this is a smooth version of that. You shouldn't really smooth because the spatial resolution isn't that great to start off with. But it kind of clarifies that you're getting out these shapes associated with the unidirectional structures that should be in here. So red here is a large value statistic, which indicates that you have unidirectionality at that voxel. And slightly more informative, but perhaps not showing up as well in the color that it should. This is a plot based on this degree of anisotropy that I said was related to the apparent diffusion coefficient. When you have blue instead of yellow, then this is indicating that there is a high degree of anisotropy, i.e. there's a single voxel which is very directional. And I've overlaid as white dots an FDR version of the test statistic for calculating which voxels were diagnosed as unidirectional. And as you see, we don't catch them all, but we're certainly catching things in the same areas. And on top of that, I've got the FDR version of both the ellipsodality and the asymmetry statistic. And of course, there should be no asymmetry in the brain because theoretically these diffusions are Gaussians, and Gaussians cannot be asymmetric. They can be ellipsoidal, but they can't be asymmetric. But you see, there are a number of dots here, and we can even look at what they look like in practice. So there are numerical approximations to do the inverse Fourier transform, which aren't super reliable, and I wouldn't base test statistics to them, but they can help us to see what's going on. And you see there's clear asymmetry here. This is close to that side than that. So this is one of the voxels that was identified using these testing procedures, sort of using FDR to make sure we're worrying about multiple hypotheses. And secondly, another one who was recognized as clearly ellipsoidal. It is also hinting towards asymmetry if you look at the test statistic. So these could be sort of not by themselves telling us anything about the structure and the connectivity of the brain, but these values of these test statistics is what you'd feed into the connectivity algorithm and help you to better connect up the voxels as part of the same structure. Okay, so it's really going bottom up, right? That's the next stage. And actually, I won't explain these because I'm running out of time. So what's the conclusions from my talk? And I've kind of not quite touched upon all the issues because I always go too slow the first time I give a talk. Some non-parametric summaries that have spatial structural features can with success be calculated. Most of the other structure people tend to get out is because they make other assumptions, like Gaussianity of the data, etc. And that's Gaussianity in the mean, not in the distribution. So we can't really expect to validate our sort of physical theory about the diffusion unless we start using non-parametrical estimates. And then we can't get out as much apparent structure as if we put in more stronger assumptions. But I think this is an important area to go into because we don't want to make false assumptions about the densities and stick in multi-tensor models which have several Gaussian peaks when it should really be a single peak with different structural features, and those would help us to do a better map of connectivity. Okay, if we were to use Gaussianity, and this is just a sort of a general comment, not something I presented here. Okay, if we're right, it works great. So people do a lot of simulation results having a Gaussian density and then estimating it. But if not, you're really getting a false degree of certainty of what the structure is like. And if you start using a mixture of Gaussian atoms for the mean, there are inherent identifiability issues because of the numerical analysis. Once you start approximating things like a sum of Gaussian bumps, this is not a well-behaved approximation. So you need to be aware of this when you start using it. And I haven't discussed this in great detail, but there also, unless you're careful, you can try to tease out too much information from the data and get out perceived asymmetries and fallacies in what could be calculated, because you need to always go back to the physical assumptions. These are the Fourier transform of a real valued object with certain symmetries. And this needs to be put in before you start calculating summaries, and some things you cannot get out from the diffusion because of the fact that you've taken magnitudes, for instance. Okay, so I'm finishing, I think, 5 minutes too late, but there you go.
So no, actually, I think the best part of your talk was about the situation where there's a single image and a single patient, and where does the 6 or 60 patients, but certainly not more, but we'd like to have more issue enter.
So it's not 60 or 60 patients. It's basically, see, if I draw it on the board, I can never go back. Now I can at least attempt it. I had a point cloud somewhere. I had Gauss. There we go. So these are 120 directions. It's measurements at each voxel in the brain.
Yes, but this refers to a single patient.
Yes.
And some slides before, you made comments.
No, I shouldn't have.
Okay, then I misunderstood those. So
yes.
They refer to these directions as well.
Yes, I'm trying to understand the structural properties of a single individual. If I wanted to make statements about the population health or the properties of the brain as deterioration due to Alzheimer's, this wouldn't be the way to go. I quite agree with you. People do that though, they get 3 brains and they start saying
no, I didn't want to discuss it, I just figured out that I should understand something which I didn't. So.
Any other questions?
Sophie, is AQ, you calculate AQ voxel by voxel, is that right?
Yes, so AQ is calculated for each voxel, and then you use summaries of the AQs to get properties across voxels.
Finally, you want to, say you are working on DWI, I mean, finally you want to get ADC map, or you want to get a similar map as a function as ADC.
The map you saw there is like an ADC map, but that's not what I'm getting at, and I should apologize because I probably wasn't very clear. I'd like to develop summaries which help you with connectivity analysis. So ADC would be one thing which could be entered into the algorithm, but I think things like the ellipsodality and the asymmetry of the diffusion are also important summaries to put in there.
So can you extend that to DTI?
So this is an extension of DTI.
But you just use DW. So your title you say is DW.
Well, DWI is a generalization of the understanding DTI. So in DTI, you have the same data, but you assume either a single Gaussian or a mixture model.
Yeah.
So you calculate the eigenvectors on the basis of the same measurement. So I could have done a DTI analysis on all of this.
Yeah, because I was a bit confused because you say you need at least 6. So I thought
that's the DTI model, exactly.
DWI. Yeah, and last question is that you say that AQ can be used to calculate ADC. The formula, but you only have 1 B.
Well, yeah, so you
But
can...
normally you need...
Yes. So if you're interested in ADC maps, you normally would do it...
You need
instead of sampling just on the sphere, it gets really cool. You sample on several shells, and you can start thinking about the approximation properties of doing estimation on several shells which have different spheres.
I was a bit confused. In your equation to calculate that, actually you interpret your result as ADC.
As a ratio ADC, yes. So the B's would cancel.
There's only 1 B,
yes.
1 over B.
Yes, because I'm doing...
Is B the gradient strength of the...
Yes.
So you only 1 B is enough to calculate YADC? So normally you need several B's to...
Yes. So I'm not doing ADC analysis. I'm saying that the summary I construct is related to the ADC measure because the ratios of 2 ADCs at a fixed B would correspond to the thing I'm calculating. So I'm not looking at non-Gaussian properties over B and do diffusion kurtosis imaging or anything like that. I'm just relating the summaries I come up with existing stuff which is in the literature. So nothing so fancy. Silence. Okay, I think that's...
So you comment when people define the MAD, they divide by 0.6745.
I should have here, didn't I do that?
Yes, you did.
Which
Why
is-
don't they just multiply by 3/2?
The point is, if you do, this is the constant that you need to get the whole thing consistent for a
Gaussian.
normal signal.
Oh, I know.
Yeah.
A big difference, but it's nothing.
Well, if you know the precise value, why would you use any other? I mean,
Well,
It's probably not precise anyway, but
Semi-facetious
I'd say that
comment. Why,
tradition from wavelets
why write
people.
down 8 significant figures when only 2? Well, silly.
No, it's recorded for posterity, so we can walk forward. Okay. Any more comments? Okay.